Okay, let's have the solution to example 5. Compute the slope and the vertical deflection of points B and C. The E is constant, Julius elasticity is constant, solved by the double integration method and by area moment method and by the conjugate beam method. So this is the beam. We have two segments of the beam with different momentum inertias. Before I proceed, if it is your first time in my YouTube channel, please don't forget to subscribe and press the notification bell if you want to be updated of my future videos, which will be helpful in your studies as civil engineering students. So here we go. First, summation versus y equals 0. So the vertical reaction at A is obviously equal to 70 kilonewtons upward. And the moment is counterclockwise. You have 40 times 3, 120 plus 30 times 6, 180. So 300 kilonewton meter counterclockwise at A. So let's have these segments for portion AB and for portion BC because they have different momentum inertias. So as I said, RA is 70 kilonewtons upward and the moment is 300 kilonewton meter counterclockwise. Since the moment equation for segment AB, we have clockwise moment. Remember the positive sign convention for moment. In the left segment, in the left section, the moment is positive counterclockwise. So therefore, E times 2I, y double prime AB is equal to 70 times x, then minus 300 times x to the 0. So 300 x to the 0 is equal to 300 because x to the 0 is 1. You should accustom to doing this because there might be a problem where the couple load is not at the origin but rather at a certain distance from the origin. So you always do that so that you will be reminded that if the value inside the parentheses is negative, we're going to ignore that. So divide everything by 2 so that we have EIY double prime y double prime AB equals 35x minus 150x to the 0. Integrating once, we have 17.5 EIY prime AB, this is the slope, 17.5x squared minus 150x plus C sub 1. That C sub 1 is 0 because C sub 1 is the slope of the tangent at point A, which is our origin. And the slope of the tangent at the origin is 0. So take note of that. Integrating again, so we have EIYAB is equal to 35 over 6x cubed minus 75x squared, then supposedly plus C sub 2. But again, C sub 2 is 0 because at A, the deflection is 0 or y is 0. So that's why we don't need to put C sub 2. Then, for the portion BC, EIY double prime BC, because the momentum inertia is just I. So we have 70 times x minus 300. There's no need to put x to the 0 because we know that. Then minus 40 times x minus 3. So that's it. Then integrating once, 35x squared minus 300x minus 20 times x minus 3 quantity squared. So plus C sub 3. So call that equation 3. So remember that you cannot set C sub 3 0 because the origin of this portion is at B. So there is a value of C sub 3 definitely. Then integrating again, so we have EIY ABC equals 35 over 3x cubed minus 150x squared minus 20 over 3x minus 3 quantity cube plus c sub 3x plus c sub 4. Now we can evaluate c sub 3 and c sub 4 later after we solve for the slopes and deflection at B. So we can now determine the slope and deflection at B by setting the value of x equal to 3 at B. Then we can solve the slope y prime AB and the deflection YAB. So when x is equal to 3 in equations 1 and 2, so in equation 1 first, so EI theta B is equal to 17.5 times 3 squared minus 150 times 3. So theta B can now be computed equals negative 292.5 over EI. So obviously it is negative because the elastic curve will bend downward and the slope would be negative as well as at C. Then when x is 3, substitute in equation 2, you can compute delta B, 35 over 6 3 cubed minus 75 3 squared. So it is equal to negative 517.5 over EI. So having found theta B and delta B, we note that the slope at B is common for portion AB and for BC only when x is 3. So when x is 3, in equation 3 and equation 4, and noting that EI y prime AB is equal to EI y prime BC when x is 3. So we have EI y prime AB is negative 292. EI times negative 292.5 over EI equals 35 times t squared minus 300 times t. This is 0, so plus c sub 3. So c sub 3 can now be computed. It is equal to 292.5. Then EIY-AB is equal to EIY-BC when x is only 3. So EI times negative 517.5 over EI equals 35 over 3 times 3 cubed minus 153 squared, then 0 plus c sub 3, which is 292.5 times 3 plus c sub 4. Solving for c sub 4, c sub 4 is negative 360. Then, having known c sub 3 and c sub 4, we can now substitute in equation 3 to solve for theta c. So EI theta c equals 35 times 6 squared when x is 6, rather, minus 300 times 6 minus 20 times 3 squared plus c sub 3, which is 292.5. So theta c is equal to negative 427.5 over EI. Then same when x is 3, we can now solve delta c into equation 4, 35 over 3 times 6 cubed minus 150 times 6 squared minus 20 over 3 times 3 squared plus 292.5 times 6 plus c sub 4 negative 360. So delta c is equal to negative 1665 over EI. So that's it by double integration method. So stand by for the other two methods. Now solve problem 5 by another method, this time by area moment method or by the use of the area moment theorems. So let's make our moment center B. You can make any point on the beam as the moment center as long as it's the simplest moment diagram by parts. So remember that RA is 70, RAX is 0, then the moment is counterclockwise 300. So this is the moment diagram by parts, considering B as the moment center. So we have, remember that this is 2I. So due to 70 times 3, 210 first degree, then divide by 2, 105 over EI. So for the 300, it's not 300 because we're going to divide by 2, so 150 over EI. Then at B, 70 times 3, 210 divided by 2, so it's only 105 over EI. Then 30 times 3, because this is just I, so it's 90 over EI here. So take note that our reference tangent would be the tangent at A, which is horizontal. So if we have to solve for the change in slope between A and B, EI theta AB, EI theta AB is automatic EI theta B, because the reference tangent at A is horizontal, represented by the green dashed line. Then this is the tangent at B. So we have theta B, which is equal to theta AB, I said. Then delta B, this is the tangent at C. The slope for the angle it makes with the horizontal is theta C. And both theta B and theta C are negative. They are sloping down to the right. Delta B is expected negative, and delta B is supposedly equal to EI deviation of point B relative to the tangent at A. But because the reference tangent is horizontal, then EI deviation of B relative to the tangent at A is automatic delta B. Likewise, EI deviation of C relative to the tangent at A is also EI delta C, automatic delta C. So EI theta AB is the area between A and B. So it is equal to 1/2 of 3 times 105 over EI, 0.5 times 3 times 105. That's it. Then minus 3 times 150. So theta AB can now be computed, negative 292.5 over EI, which is the same as before. Then, for EI division of B relative to A is automatic EI delta B because the reference tangent is horizontal. So we simply sum up moments of the areas between A and B with respect to B. So we have 1/2, 0.5 times 3 times 1, or 5 times 1. The moment arm is 1, 1/3 of 3. Then minus 3 times 150 times 1.5. Half of 3 is 1.5. So delta B is equal to negative 517.5 over EI, just like before. Then considering A to C, EI theta AC is automatic EI theta C. Then it is equal to supposedly negative 292.5, or if we go back to computing areas, quantity 0.5 times 3 times 105 minus 3 times 150, then you will just add this negative area, minus 0.5 or 1/2, 3 times 90. So theta C is equal to negative 427.5 over EI. And finally, for delta C, we have division of C relative to the tangent at A. So we simply compute the moments of this area between A and C with respect to C. So it is 0.5 times 3 times 105 times 1 plus 3 is 4. The moment arm is 4. Minus 3 times 150, 1.5 plus 3 is 4.5. The moment arm is 4.5 for the second area. Then for the third area, 2/3 of 3 is 2. So the moment arm is 2. So minus quantity 0.5 times 3 times 90 times 2. So computing for delta C is equal to negative 61665 over EI. Then we proceed to solution number 3, which is by conjugate P method. So we use this moment diagram by parts from the area moment theorems, and we just revise the supports. So this fixed end becomes free, and this free end at C becomes fixed. So that's it. Now, by definition, theta is shear of this conjugate P. So because this is left and this is right section, so if we consider AB, the positive slope is, or the positive shear is downward. Then the positive, considering AB, the positive moment is counterclockwise. So let's assume all slopes and deflections positive. So that's one. So considering AB, we sum up forces Y, we can solve theta B. This is theta C. Considering B and C, B is left, C is right. So theta C is positive downward. Then positive moment is counterclockwise. So that's delta C, which is moment of the conjugate B. interpretation. So considering AB, summation forces y equals 0, then we have, so this positive area is upward, negative area is downward, remember that. So we have quantity 0.5 times 3 times 105 over EI minus 3 times 150 and minus theta B equals 0. So solving for theta B is negative 292.5, is the same as this and the same answer as that of the double integration method. Then summation moment about B, still considering AB, clockwise positive. So we have quantity 0.5 times 3 times 105 times 1 minus 3 times 150 times 1.5. The moment arm is 1.5. Then minus delta B equals 0. So solving for delta B, it is equal to negative 517.5 over EI, just like before. Then this time considering BC, so we transmit by action-reaction principle. So theta B is now upward here because this is the left segment if we consider BC, and delta B would now be positive clockwise. So take note, we consider theta B upward, delta B clockwise. And if we consider BC, if we sum up forces vertical, we can solve theta C. So theta B, but theta B is negative, although it's upward, negative 292.5, then minus 0.5 times 3 times 90 over EI, then minus theta C equals 0. So theta C is equal to negative 427.5 over EI, just like the answers before. And finally, summation of moment about C equals 0, considering clockwise as positive, then we have theta B, which is negative 292.5 over EI times 3 minus quantity 0.5 times 3 times 90, then the moment arm is 2 minus 0.5, quantity 0.5 times 3 times 90, and the moment arm is 2, then plus delta B, but delta B is negative 517.5. That's it. Then we have minus delta C, because this is counterclockwise, we assume clockwise as positive, then equals 0. So solving for delta C, it is equal to negative 1665 over EI, just like before. So that's it, and this verifies that we solved the problem correctly because all the answers are the same correspondingly.